We're interacting with databases all the time, probably more than we even realize. But what happens when thousands or even millions of us are all trying to use the same data at the exact same time? It's like a huge crowd all trying to rush through a single doorway. Well, in this explainer, we're going to pull back the curtain on the powerful systems that manage all that chaos, keeping our data consistent, correct, and most importantly, secure. Yeah, that's the perfect question, really. It gets right to the heart of the whole problem. It seems like this should be happening constantly, right? But it almost never does. And the reason why isn't some kind of magic. It's very much by design. Databases have a very specific set of tools to handle this exact situation. And there's a name for this, right? It's called the concurrent update problem. It's one of the biggest challenges for any database administrator, the DBA. Because if you don't manage it properly, the consequences are very real. We're talking double booked flights, oversold concert tickets, inventory systems that are just completely wrong. It's chaos. So, how do databases stop this digital free-for-all from happening? Well, it all comes down to a really powerful set of control mechanisms that are designed to coordinate every single action. Let's dive into the first and, honestly, the most important tool in the entire toolbox. The foundation for all of this is something called the atomic transaction. You can think of it like an unbreakable pact. A transaction bundles several steps together, like, say, checking for that airline seat, reserving it, and then processing your payment. The atomic part is the crucial guarantee here. It is all or nothing. Either every single one of those steps succeeds perfectly, or the entire operation just vanishes as if it never even happened. And the cool thing is, developers get to control this directly using S2L in what's kind of like a three-step dance. First, you start with begin transaction. That kicks everything off. Then you do all your work, your inserts, your updates, all of it. And finally, you get to the big decision point. You either commit, which makes all those changes permanent, or if anything went wrong along the way, you roll back, and it's like nothing ever happened. The database is left completely untouched. Right. Okay, so the transaction is the wrapper. It's that all-or-nothing container. But what's the actual mechanism inside that wrapper that stops two different transactions from stepping on each other's toes? That is the key question. And the answer is a concept called resource locking, which comes in two completely different philosophies. First, you have pessimistic locking. This is basically like calling dibs. It assumes a conflict is probably going to happen, so it locks the data before it does any work. No one else can touch it. Then there's optimistic locking, which is more of an ask for forgiveness, not permission approach. It assumes conflict is rare, so it does all the work first and only at the very last second does it check if someone else changed the data. If they did, oh well, the transaction fails and you just have to try again. And we can get even more specific with the types of locks. A shared lock, well, think of it like being in a library with a reference book. Lots of people can gather around and read it at the same time, but nobody is allowed to write in it. Now, an exclusive lock is like actually checking that book out of the library. Now you, and only you, can read it and write in it, and nobody else can even look at it until you're done. Okay, but wait a minute. If all these transactions are constantly locking different resources, couldn't that create its own kind of problem, like a digital traffic jam? What stops the entire system from just grinding to a halt? Well, that leads us to the dark side of locking. And this is the villain of our story, deadlock. It's sometimes called the deadly embrace, which is pretty dramatic but accurate. So imagine you have two transactions. We'll call them A and B. Transaction A locks a resource that B needs to finish its job. But at the exact same time, transaction B has locked a resource that A needs. Now they're both stuck in this standoff, each one waiting for the other to release its lock. And without some kind of intervention, they would just wait there forever. Thankfully, the database management system, the DBMS, it acts like a referee here. It has these built-in algorithms that are constantly on the lookout for these standoffs. And when it finds one, it has to make a tough call. It picks a victim. One of the transactions is chosen to be aborted and rolled back, which releases its locks and lets the other one move forward. Then the application that started that failed transaction can just, well, try again later. So all of this stuff, transactions, locks, deadlock management, it all serves a higher purpose. It's all about meeting this gold standard for reliability. These are a set of core principles known by the very famous acronym, ACID. First up, A is for atomic, and we've already kind of covered this. It's that absolute all-or-nothing guarantee. And this is so critical. It prevents those weird partial updates that could leave your database in a completely broken state. Next up, C is for consistent. This just ensures that a transaction can only ever move the database from one valid state to another. It basically means the database has to follow its own rules. So you can't, for example, create an order for a customer that doesn't actually exist in the database. Then we have I for isolated, which is absolutely vital for making all of this work with multiple users. This guarantees that the messy, intermediate steps of one transaction are totally invisible to all the others until it's officially committed. In short, you never get to see anyone else's half-finished work. And finally, D is for durable. This is basically the database's pinky promise. Once it tells you that a transaction has been committed, that data is safe, it's permanent. Even if the server loses power a millisecond later, your committed data will be there when the system boots back up. Now, that isolation principle is key, but getting perfect isolation can be really expensive on performance. So systems actually let you choose a level of isolation, which means you're balancing performance against preventing these specific weird data problems. A dirty read is seeing data that hasn't been committed yet and might get rolled back. A non-repeatable read is when you read some data and then you read it again a second later and it's changed. And a phantom read is when you run a query and new rows just seem to appear out of thin air. And you can see that trade-off right here in the 4 standard SQL isolation levels. As you move down this table, the protection gets stronger and stronger. At the very bottom, serializable is like Fort Knox. It prevents all of these weird problems, but it can really slow things down. At the top, read uncommitted is super fast, but also super risky. And that's exactly why most databases defaults to read committed, right in the middle. It's a pretty sensible compromise. Okay, so our data is consistent, it's reliable, but is it safe? Making sure the data is correct is one huge piece of the puzzle. Protecting it from people who shouldn't see it is an equally critical challenge. And you know, modern database security isn't just a single password. It's what we call a defense-in-depth strategy. It has multiple layers. It starts with physically locking up the server hardware itself and goes all the way up to defining the very specific actions each individual user is allowed to perform. So, inside the DBMS, a database administrator will manage access by creating user accounts and then grouping them into roles, like, say, a sales clerk role or an inventory manager role. Each role is then given very specific permissions. A clerk might be allowed to create new sales records, but they're definitely not allowed to delete old ones. This is the principle of least privilege in action. You only give users the absolute minimum access they need to do their jobs. But one of the most famous threats out there doesn't even attack the database directly. It attacks the application that talks to the database. It's called a SQL injection attack, and it's a deviously simple but nasty trick. Okay, so imagine an app has a simple text box asking for a user's name. It's expecting something like Benjamin Franklin. But a malicious user comes along and types in the name, followed by the SQL command, or true. Now, if the application isn't built securely, it might just stitch that text directly into its database query. And just like that, boom, the logic of the query is completely broken. That or true part makes the condition true for every single row, potentially letting the attacker dump the entire user table. So at the end of the day, what this all really comes down to is a complex balancing act. Everything we've talked about, concurrency, locking, ACID properties, security, they're all like knobs that the DBA has to constantly tune. If you crank up the performance knob too high, you might risk consistency. If you over-index on security, you might slow everything down. It's a perpetual trade-off. And that really brings us to a final, and I think provocative thought. The ACID principles we talked about were really defined for these big, centralized databases. But in today's world of massive, globally distributed big data systems, some new designs actually and intentionally relax those strict rules on consistency, all to achieve higher speed and availability. And it forces us to ask, is perfect consistency always the ultimate goal anymore? What trade-offs are we willing to make for the data challenges of the future? If you enjoyed this breakdown of how databases really work, please go ahead and like, share, and subscribe for more explainers on complex topics. Thanks for joining us.